Okay, ionic compounds are not the only kind of compound that we can make. Typically for ionic compounds, we put together a metal and a nonmetal, or we throw in a polyatomic ion. But we also really haven't figured out what a polyatomic ion is made of, because then the whole thing has a charge, but what about the other atoms that make it up? Are they also ions? Well, if we look at it, they don't add up the charges right. Like if you take something like the sulfate ion, that's SO4, it should come out with a -2 charge. But I mean, each oxygen has a -2 charge, and each sulfur has a -2 charge. So that's like a lot of negative charge right there. That does not equal -2. So something else has to be going on to make that polyatomic ion. And it's the other kind of bonding we're going to be talking about in this video. Okay? Rather than always doing a give and take of electrons, sometimes we have to share so that the atoms involved in the bond, okay, both have ownership over the electrons involved. Okay? We call that covalent. Oops. Since we are taking the valence electrons of each atom and kind of crossing over the electron clouds, kind of meshing them into each other, so they kind of come together and they cooperate to help each other out. So covalent, like co as in together, helping each other, and then valent as in the valence electrons. Okay, a molecule is just a word for a group of atoms that typically bond covalently. That's kind of the we don't really call ionic compounds molecules when they group up. It's specifically for covalent stuff. Okay, so this first example, we're going to show how the element fluorine can come together with multiple atoms and just kind of stick together and become something that is still happy without a give and take of electrons. Okay, so let me draw out two Lewis dot structures of fluorine. So I'm going to make one fluorine right here. I'm going to give it 7 electrons. Now, this isn't something that we've talked about as much probably before, but if we want to make sure this stuff kind of turns out well, a good way to draw your valence electrons around your atom is to try and spread them out as much as possible. This is something that we did in electron configurations a while back, but we haven't really touched it much since then. So I usually just kind of go around in a circle until I get everything kind of put in, and we only pair stuff up if we need to. So we go around and kind of do instead of 4 instead of 4 and so on and so on. Okay, so this is one fluorine atom, one Lewis dot structure of fluorine. Let's do another. There, 1, 2, 3, 4, 5, 6, 7. Again, avoiding pairing up if we can. Okay. Now, if we were trying to treat this like an ionic compound, well, fluorine is very close to an octet of 8 valence electrons to mimic the electron configuration of neon. So, hey, fluorine's got 7, needs to get to 8. I just need to take an electron from something. So, I could give one of these electrons over to this fluorine, which would give it 8 valence electrons. It would have a negative charge, and that one's happy and good to go. But then this fluorine is down to 6 valence electrons, which is worse for it. It was looking to gain an electron, not lose one. So this is worse off. This is going to be more unstable. It's going to be higher in energy. It's not going to be a good option overall. So sure, we might be able to make one thing happy, but not the other. We want our molecule to be made of stuff that mutually benefits. So this isn't a good strategy to use. Instead, we want these guys to share their electrons, so they both have ownership over them. Oops, just made a bunch of squares. Let's take those out. Draw my valence electron back in there. Now let me see if I can scooch this guy a little bit closer. Oops. Oh, I got fluorine, but not its electrons. Oh, I got most of them. There we go. Nice. Okay. So if I want to make these guys happy, they're going to have to share their valence electrons in what we call a covalent bond. We show that by drawing a line connecting a pair of electrons. Something like that, to kind of show these two things now have ownership over those two electrons. So this fluorine has its original 1, 2, 3, 4, 5, 6, 7 valence electrons, plus it also gets ownership over this 1 valence electron from fluorine. So it ends up with a total of 8 valence electrons. This fluorine over here has its original 1, 2, 3, 4, 5, 6, 7, plus this 8th one that it's also got ownership over. So, ooh, really messed up that valence electron. Let's try that again. So in total, it's got its original 7 plus 1 more for a total of 8 valence electrons. So these both can get to an octet without having to do a give and take. Okay, all we have to do is share one pair of electrons between these guys. One atom kind of pitches in one atom, or I mean one electron, one atom pitches in another electron, and then together they make a covalent bond. And so they both have ownership over this, so they essentially both gain an electron. Now because of this, we don't end up with any charges because there isn't actually a give and take. They still have the electrons they had before. They're just kind of now close enough to each other that they can both benefit. Sometimes you'll see this drawn strictly with the Lewis dot structures. 1, 2, 3, 4, 5, 6, 7, something like this. And then, I zoomed in on accident. Zoom out. There we go. Too far. There we go. Okay, and I'll put another one just right next to it. Do 1, 2, 3, 4, 5, 6, 7. So that way you can kind of see how these guys would kind of overlap. This kind of looks more like how we think of atoms, kind of as circles or spheres. So that might kind of work better in your head. But traditionally, nowadays, we do this with covalent bonds like this, as a line connecting a pair of electrons. Okay. Now, it's sort of a fashion faux pas in chemistry to leave the dots with your lines. So typically, we kind of get rid of each of the original valence electrons. We don't kind of like cap them off and be like, there's a valence electron there, and put a dot there and put a dot there. Instead, we just leave it as a line. That way we don't accidentally confuse and kind of recount electrons. It's like, is that one that's in the bond, or is that one that was already there? We don't need to worry about that. A line counts as 2 electrons being shared. This is our covalent bond. And it represents a pair of electrons. Specifically, we use the valence electrons. The inner electrons we call the core electrons don't do a whole lot here. Okay. Zoom this out a little bit more. Okay, so in order to get our molecule here, our group of atoms bonded by covalent bonds, in order for these 2 atoms to be happy in this molecule, we only needed one kind of pair of electrons to be shared between them. So one pair of electrons is shared. Okay, we call this a diatomic molecule because this is a diatomic element. We just have 2 atoms of the same element, and they covalently bond, so we can call it a diatomic molecule. Okay, and the way that we just have one line here, one pair of electrons, okay, is what we call a single bond. Whoops. Okay. You could be more specific and say a single covalent bond, but typically if you just say a single bond, people know what you're talking about in chemistry. So this is a single bond. It's just one pair of electrons. Okay. Where we show it as a line connecting the 2 dots. and then we just kind of end up erasing the dots. All right. So once we make this bond, each atom in this molecule ends up with 8 valence electrons. Both of them end up following the octet rule, which is a good sign that these guys are now more stable. Okay, this is a more favorable way for fluorine atoms to arrange. Rather than on their own, they'll group up in these diatomic molecules. Okay, so this is good. This is good to know. We've made something more stable, which is basically how chemistry goes and proceeds. It's all about trying to make things more stable. Let's look at another example. Let's skip past bromine. All right, yeah, we're going to look at oxygen next. They make a covalent molecule out of 2 atoms of oxygen. Okay, well, let's draw out what oxygen looks like. Oxygen here, and it's got 1, 2, 3, 4, 5, 6 valence electrons, since it's in the 16th column of the periodic table. Let's draw another one over here. 1, 2, 3, 4, 5, 6. All right. So if they're each starting with 6 valence electrons, they're not too happy as it is, and we can probably guess that a give and take is not going to work here. So instead, let's try and make a covalent bond. All right. Well, now each oxygen has its original 1, 2, 3, 4, 5, 6, plus a 7th one, which is better, but we're not quite at an octet yet, so we're not quite there. Well, we're not limited to just make one covalent bond, which is kind of interesting. If oxygen needs another electron, why don't we just share another? This oxygen on the left is like, hey, I'll give up an electron to kind of put into the pool, if you will. And, okay, yeah. So we can draw another line to connect these electrons here. And now each oxygen has 8 valence electrons. We started with 6. We're now sharing 2 pairs of electrons. So each oxygen now has ownership over 2 extra electrons. Okay, no give and take, no charges on these ions. This is our covalent molecule. Now this is kind of messy. So here's something that you can do to kind of help with that. We can kind of rearrange our electrons a little bit to make this look a little nicer. So you might do kind of an initial drawing to see how many bonds it takes, and then you can kind of clean up your structure. So like, I know I'm going to need 2 electrons over here to make my bonds. Okay, and maybe I can kind of line this up a little better so that they're going straight across. Oops, not quite. Try there, that's a little better. Okay, so now that I have this kind of lined up better, when I draw my bonds across, there, and there, just looks a little bit better. Okay, and you can rearrange these electrons however you want to kind of clean this up. So if you'd like to show that there should still be 1 electron unpaired down here and over there, you could do it like that. Sometimes you'll see people that like to group these up. And that's also fine. We don't spend a lot of time on figuring out how many electrons are left paired or unpaired because it's honestly a little too confusing, and there's not a good kind of trick or rule or guideline to it that makes it kind of simpler to do. It's something that you kind of get used to the more you see how molecules are supposed to be drawn and the more you practice them. So know that the way that we leave these extra valence electrons on the outside, whether they're paired or not, is not a huge deal. But it is good practice to kind of draw them out neatly. So try not to leave a bunch of diagonal lines all over. Don't cross lines or anything like that. Okay. Now in this case, we have 2 covalent bonds. okay, which means we are sharing 2 pairs of electrons. All right, we call this a double bond or a double covalent bond. Okay, so in order to get oxygen to have 8 valence electrons, it needed its original 6 plus 2 from the other one, 7, 8. And this oxygen had its original 6 plus 7, 8 right there. So we needed more than one covalent bond. So we made 2 covalent bonds. We call that a double bond for short instead of saying 2 covalent bonds. Okay, so to make diatomic oxygen, to make a molecule out of 2 oxygen atoms that are happier than the original 2 atoms, we just draw 2 lines in between them. And again, let's see if I can get precise enough with my eraser without getting rid of the covalent bonds. Yeah. We can get rid of the original electrons so that way we don't accidentally recount them. Most of the time, I'm not super nitpicky about this, especially at the beginning, because it gets used to, you're just practicing, you're just starting out. One of the big things I see that you should try to avoid is leaving space in between the electrons when you draw your line. So I see this a lot where people will do something like that. Okay, now that really does look like you've got extra electrons because this is supposed to be a pair of 2 electrons, but then you've still got this guy here and you still got this guy here. That looks like 4 electrons. It looks like you just kind of produced them out of nowhere, at least from a chemist's perspective. So you might look at it and say, oh, well, they're just connected, but it can be a little bit confusing. So to avoid that, I would try and erase your dots or make sure at least they are completely connected. Okay, this is the goal, to have no dots left on the ends of your lines, but c'est la vie. So when we make this oxygen molecule, we needed to share 2 pairs of electrons to make this diatomic molecule, 2 atoms of each element. We've got 2 atoms of oxygen there. Okay, and those 2 pairs of electrons being shared are called a double covalent bond, or just a double bond. Okay, and as a result, each atom ends up with 8 valence electrons, which is happier and more stable than what we started with. Okay, we also end up mimicking neon with this electron configuration by kind of having ownership over 2 extra electrons compared to what oxygen usually starts with. Okay, but no give and take is involved and no charges are involved here. We don't have any ions. Everything is still neutral. Okay, I'm going to show you one more example. Make a covalent molecule out of 2 atoms of nitrogen. Okay, well, nitrogen starts with 5 valence electrons. Oops. Spread them out a little bit more. 2, 3, 4, 5. Let's do this one in blue. It's in column 15, so 2, 3, 4, 5. 5 valence electrons. Okay, and again, I'm trying to get them both to an octet of 8 valence electrons. So if I've got 5 valence electrons to start, if I make 1 covalent bond, that would get these guys to 6 valence electrons each because they each get ownership over 1 more electron. Okay, I could do a double bond to get them to 7 valence electrons, which is still closer yet, but not quite there. All right, and finally, to get them to 8 valence electrons, I can do a triple bond. All right. So with this, each nitrogen atom is now more stable. It's got ownership over its original 5 electrons plus 3 more. But again, we should probably redraw this a little bit. This is a little bit clunky. So I'm going to rearrange my electrons a little bit. Since I know I need to share 3 pairs of electrons here, I'm just going to line up three electrons right here. So they are ready to go. All right. We like to make bonds close to each other, not spread out. Otherwise, it gets confusing when you have more than just two atoms bonded together. So right between these, I'm going to do a bond and a bond and a bond. So I've got 3 bonds. Okay, that's 3 pairs of electrons being shared. You might be able to guess we call that a triple covalent bond, or just a triple bond. Okay, sometimes you'll see this where we move this pair of electrons over to the other side. Move this to the other side. So it's kind of out of the way. One way you can kind of tell how your structure is supposed to kind of work out, we typically throw in unpaired electrons first for bonding. So if you remember my original structure of nitrogen, had a pair of electrons and then boom, 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 and had 3 sitting out just like that. Well, you can probably guess that these 3 electrons here and here and here are going to be ready to go for bonding. For our oxygen one, we had 2 sets of electrons that were already kind of paired up as we kind of went around and tried to spread them out as much as we could. So you might say, ooh, well, I've got these 2 electrons that are unpaired. That's a good sign that they're ready to bond with something. Okay? And even with the fluorine we started with, we had 1, 2, 3, 4, 5, 6, 7 in total. One of them was unpaired. That's a good sign that that one's going to be the one for bonding and not the paired ones. Okay? So if you want your drawing to come out clear from the get-go, I would try and bond your unpaired electrons first. Oh no, I lost the bond on that one. And that one. Let's draw those back. I've got rid of my dots. Okay. So each atom in this ends up with 8 valence electrons. Nitrogen with its original 1, 2, 3, 4, 5 plus 6, 7, 8. 1, 2, 3, 4, 5 plus 6, 7, 8. And that other set there. Okay, so they each end up with an octet, 8 valence electrons. Let's keep color coding consistent, or it will drive me crazy. There we go. Okay, now you might look at this and say, well, what if we had carbon and carbon? And they each have 4 valence electrons. So they would need to make 4 bonds, right, to get to 8 valence electrons. Okay, I see where you're going. So could they make a quadruple bond and connect all of these? Well, yes and no. Okay, no, in that we don't have a quadruple bond typically for carbon. Recent research shows that it might be possible, but typically in the stuff we deal with, unless we put it in some very odd circumstances, carbon doesn't do a quadruple bond with each other to make a diatomic molecule. If you're wondering on why, I would recommend taking advanced chemistry, where we look at more on the orbitals that are involved in bonding, which can kind of shed some light on how some atoms come together and how their electrons can be shared in ways that they can't be shared as well. Okay, but carbon can still make 4 bonds. We just don't usually see it between 2 atoms at the same time. So I could have carbon that, oops, got my eraser out still. I could have carbon that makes 4 separate single bonds, or I could have carbon that makes 2 separate bonds and a double bond, or I could have carbon that does a triple bond and a single bond, or 2 double bonds, or something like that. Okay, so it can still do a total of 4 bonds, and it will a lot, but we just won't see it all between just 2 atoms of carbon. Okay, we will see a couple examples in the next assignment where we step this up a little bit, but for now, hopefully that gives you the basic idea of how covalent bonding works and how we get some elements to be more stable by pairing them up with themselves. Okay, and we call these diatomic molecules.